All right, this is going to be a video about simple harmonic motion, which means motion that has a regular period, vibrations, and waves. So basically all kinds of things that have frequencies and periods. So I have two springs here. I have a green one, which I wrote down the spring constant for the green one is 50. That's 50 newtons per meter. That means that to stretch that spring, 1 meter would take 50 newtons, which we don't plan on stretching it that far. My red spring has got a spring constant of 25 newtons per meter. So if I put a 1 kilogram weight on the red one, and I started oscillating, you can see that it has a regular period. There I increased the amplitude of its oscillation a little bit. So you can see it has a regular period. Now, the green spring, I'm going to put a smaller weight, only 500 grams, a half a kilogram. And you can see that that has a much lower period and a much higher frequency. The green spring is a stiffer spring. So they might be close if I switch them around. So now I have the heavy weight on the stiff spring, and I have the light weight on the not as stiff spring. The equation for the period of a pendulum, or not of a pendulum, of a spring, is 2 pi the square root of m over k. M stands for the mass. So the more mass, the longer a cycle is going to take. But the stiffer the spring, the shorter the cycle, because that's in the denominator. Frequency is just the opposite. Frequency is 1 over 2 pi, the square root of k over m. Right? Why is everything upside down? Because frequency is 1 over the period, and period is 1 over the frequency. The seconds per cycle is 1 over the cycles per second. Simple pendulums are also a type of simple harmonic motion. So what variable affects the period of a pendulum? Does it matter if I change the angle that the pendulum is released from? Does it matter if I change how much mass is on my pendulum? I have some washers on here right now. There, now no washers. You happy? It's looking kind of similar. How about if I change the string length? One of the reasons why the string length is the only thing that matters is because if I go to a further angle to the side, sure, I have a further travel distance, but I get going faster at the bottom. So changing the angle just changes the speed at the bottom, but it doesn't change the amount of time it takes to make a complete cycle. Changing the mass doesn't matter because we've already learned that mass does not affect speed of a falling object. The speed is the square root of 2 times gravity times the height. So changing the mass doesn't affect it, just the string length. So if I have a really short string, I can expect a really short period. For a pendulum, the period is 2 pi times the square root of L over G, which makes the frequency 1 over 2 pi square root of G over L. I always remember these because frequency starts with an F, which comes first in the alphabet, and so G goes on top because that comes first. T comes after F in the alphabet, and L comes after G. Same thing over here for springs. T comes after F, and M comes after K. So if you're having a hard time remembering these, and you should remember that they are the opposite, or the inverse. Frequency and period are the inverse. So frequency is the cycles per second. And period is the seconds per cycle. And for period, we use a capital T. It's a special kind of time. And for frequency, we use an F. Another way that we can say cycles per second is we say hertz. That's the unit for frequency, is hertz. So period is the time for one complete cycle. So for a spring, it'd be the time to go down and all the way back up to where you started. For a pendulum, it's the time to go all the way over and all the way back. One complete cycle. There's a third thing that we use for simple harmonic motion, and that is a rotating or revolving system. So if you look at this tape, the time for it to come back to where it started at the top is the period, the time of one cycle. For the moon, the period is 28 days. It takes 28 days for it to be in the same spot in its revolution around the Earth. For the Earth, the period around the sun is 365 days. So we also have periods for rotating and revolving systems. So simple harmonic oscillators are things with a regular period. If something is vibrating with a regular period, it can be the source of a wave. A vibration is basically just a wiggle in time. It's something that's just going back and forth with a regular period in time. If you allow that vibration to move outward through space, you get a wave. So if I just keep going up and down and now I move through space, it automatically turns into a wave. So a wave is a way that you can transfer energy from a vibration. So a vibration is the source of a wave. And a wave is a means of transferring energy through space. There's really two ways in physics that we can get energy from one point to another. One of them is particles. If you think of like pool, I send the cue ball into the 8 ball, that's a particle moving. Or electricity, which we've learned about. You might have electrons moving, those are particles, although we can also think of them as waves, which we'll learn about in this class. But it's like a particle moving with energy. A wave, the energy is moving, and it might be moving parallel to the direction that the medium's going, or it could be moving perpendicular to the direction that the medium's going. Here, like if these were water waves, the medium would be going up and down, and energy would be going sideways. Probably have noticed this before, like if you're in a raft on a windy day, the raft is going up and down. Your bobber's going up and down. The water doesn't all arrive at the shore and now the lake's empty, right? Energy arrives at the shore. But the water mainly goes up and down for what we call transverse waves. Right? We've already learned that frequency is the cycles or the waves per second. Wavelength is the meters per wave. So what would happen if we were to multiply meters per wave by waves per second? We would get meters per second. So the wavelength, we use the letter, that's the distance from crest to crest, we use the letter lambda to represent the wavelength. It's a Greek letter. Lambda times the frequency is speed. Or usually we write it V equals F times lambda. This is the most important equation for waves. And you might think, oh, so all I need if I want a wave to go faster is a higher frequency. But we know that's not true because in sound waves, if you speak with a higher pitch, it doesn't get there sooner. You don't hear the flute before you hear the tuba. The frequency goes up and automatically the wavelength goes down because the only thing that determines the speed is the medium. The medium determines the speed. So if you go through a different medium, like sound going through maybe water instead of air, the sound wave will travel faster in water. That's why when you're underwater, a lot of times you'll think that maybe a boat is approaching really close, but it's still a long ways away when you surface. Sound even goes faster through steel. Light actually goes fastest in a vacuum, and light waves go slower as they get into more dense mediums. So as you change the medium, you change the speed. But the frequency generally goes up and the wavelength goes down, or the frequency goes down and the wavelength goes up, and you usually get the same speed. We're going to be talking about sound, and the speed of sound in air is 343 meters per second if it's about 20 degrees Celsius outside.